this test. And then depending on how much time we have left, I can go through some of the material from the previous tests as well. All right. Yeah, so I put all the stuff in. Yeah. Okay, so um, let me tell you about the test. I think there were like 360 or 70 points total out of the however many problems we had. 22 problems. So, yeah, I put all the grades in and the homework that I have. The only thing I haven't really put in is I have asked you for notes, and I'm going to use that kind of as like a extra credit that'll move you to possibly to a higher grade if you need a point or two. There are a couple of you that have 89 averages, and so that'll be enough to bump you up if you don't do it by the final exam. Bump it up. I may give you a little bump there. Um, I've got your test if you want to take it. I'll put it in the library. That's the one that you, number 2 retake. So I've got that ready for you. So the review will basically be the review. The review on the material that we just covered in the last 2 weeks. I'll put a short video together telling exactly what you need to know for that. But the rest of it will be basically looking at stuff from the previous tests. And I've got basically test number 2. This is your test, so I won't work exactly these problems, but I know what kind of I have test number 2 here to use as a basis if anybody has any questions about how to do certain problems from test 2. Okay, so let's look at test number 3 here. So the first 2 problems you were supposed to plot the exponential function and the logarithmic function. So the exponential function we had was f of x equals 2 to the x, and the table was what size? Something like that. And so the x values and y values I was looking for were -1, 0, 1, and 2, and the numbers you should have gotten were 1/2, 1, 2, and 4. And if you wanted to do one more, you could do 3, which would be 8. So this is x to the -1 power, or 2 to the -1 power, 2 to the 0, 2 squared, 2 to the first power, 2 squared, 2 cubed. So those are the points. And then need a piece of graph paper. So let me pull that out. So if you plot those 4 points or 5 points, you get this one, which is -1, 1/2, 0, 1, 1, 2, 2, 4, and if you did the next one, it'd be 3, 8. And so, it goes along the x-axis but doesn't cross it, and then it increases like that. So that was the first problem. The second problem was the logarithm function. So f of x equals log base 3 of x. And again, you can make up a table. And so you have x and y, or f of x. In this case, the y's are the ones you have -1, 0, 1, 2, and 3. And the corresponding x values would be 1/3, 1, 3, 9. This would be 27, which would be off the screen. But those are the values, because they're, the logarithm and the exponential function are inverse functions of each other. So it's easier to do this, fill this column in first, and then do the corresponding x values. So if you plot those, you'll get, let's see, -1, a third, -1, 1, 0. What's next? 1, wait a minute, did I do that right? Yeah, 1, 0, 3, 3, 1, and 9, 2. And so you bump up against the y-axis instead. You come up like this, and you go like that. So that's the log base 3. If I had log base 2, if I did that, I'd have, instead of a third here, I'd have a half, and then I'd have 2, and then you'd have 4, 2, and 8, 3, like that. So that would be log base 2. So that's how you get the plots. So you, first case, use -1, 0, 1, and 2 for the x values, and for the logarithm ones, you fill out y first and then go the opposite direction. Okay. Now, as far as the third problem, so the parent function was just the natural log exponent e value, and the transform function was -e x squared plus 2. So because you have the negative sign out in front of e, that gives you an x-axis reflection. And the plus 2, which is not inside here, it's not part of the exponent, but it's just added on, that's going to be plus 2 in the y direction. Now if I had e to the x plus 2 up here, then you'd have an x direction shift. Okay, so that's all I was looking for there. The next one, we had the function was the natural log function, and the transform function was the natural log of -x plus 2, and nobody remembers this, and I don't know how. I've talked to Ms. Pratt, and she said nobody listens to her either. You factor out a negative sign. Actually, there might have been one person that listened to me, but you factor out the negative sign inside the parentheses anytime you have a negative x inside the argument. And the reason you do that is because this gives you the right transformation in terms of the shift, the x shift. So because the negative sign's inside the function, you have a y-axis reflection. And because I'm subtracting 2, that means it's plus 2 x-axis or x direction shift. Now, some people didn't factor out the negative sign and still said that it was the right answer. And what that led me to believe is you plotted it on your calculator and then you said, oh, it's, most people just said it was -2 because they didn't factor out the negative sign. But I think somewhere I saw somebody who didn't factor out the negative sign and still said it was right. And the only way you can do that is to plot the function and look at the graph, and then, but what I'm looking for is for you to do that. So did you, and then you forgot? Yeah, I don't know why it's such a hard thing for people to remember, but it is. Okay, the next one is you actually have to plot them. You have log base 2 of x for your parent function, and you have your transform function is negative log base 2 of x plus 2 minus 2. So this transformations are, again, the negative signs out in front instead of inside. So that means you have an x-axis reflection. And because we have a positive x, we don't have to factor out a negative sign, so we just leave it as it is. So you have -2 x direction shift and a -2 y direction shift. So those were the two transformations. And so then when I asked you to plot them, so now when you're dealing with exponential or sort of logarithmic functions where you have the shift, the best thing to do is to shift the axis and draw it relative to the shifted axis. So we're going to shift the x-axis or y-axis 2 units negative in the x direction, and we're going to shift the x-axis 2 units in the y direction. So that's my new coordinate system basically. So if you plot your parent function with the black axis, you're going to have a half, 1. So it's going to, like we just talked about how to do this. So it's the logarithm of 1 is always 0. The logarithm of 2 in this case is 1. 2 to the first power is 2. And then you go over 1, 2, 3, 4, and up 2. And then you go over 8, up 3. So that's the parent function. Looks like it's kind of like that. So that's the natural log, or the log base 2. So what's going to happen is this thing's going to flip over the newly transformed axis, but relative to this new origin, the red origin versus the black origin, we can keep the same relative position. So this x-axis intersection is going to correspond to here on the new axis. So this line corresponds to that line. You can see how it's down 2 and to the left 2. This point here, which was 1/2 -1, instead of going 1/2 -1, you're going to go 1/2 +1. So that's there. This point, which is 1, 2, 1 up, this is going to go 1, 2, 1 down. The next one is 1, 2, 3, 4, 2 up. So we're going to go 1, 2, 3, 4, 2 down. And then this one, same thing, you go 8. So 1, 2, 3, 4, 5, 6, 7, 8, down 3. And so it should look something like that. And again, some people, I think, just plotted them because the plot didn't agree with what they said over here. So they just said, oh, I'm going to plot them, but then they didn't really know what they were doing. So, okay, so that is problem number 5. The first 5 problems were all worth 20 points. Just stop me if you have any questions. Okay, number 6. So we started with this log base 4 of x cubed square root of y divided by 4. So we can split this out using the properties of logarithms. So you have log base 4 of x cubed plus log base 4 of the square root of y minus log base 4 of 4. And then you can bring the exponents out. So instead of log base 4 of x cubed, it's 3 times log base 4 of x. Here, this is the same as y to the 1/2 power. So you factor out the 1/2. And the last one is 1. Log base 4 of 4 is 1. So anytime you have the same base and this, because that's what that's saying is, what do I need to raise 1? What do I need to raise 4 to get 4? Well, the answer's to the first power, so that's why that's 1. So a lot of people got to this point, but then forgot that one extra step, and I took a few points off to that one. Okay, the next bunch, I give you them in one form, I'm going to ask you to do them in the other. So remember, the exponential base is the same as the logarithm base. The answer becomes the argument, and the argument becomes the answer. Except I wrote something wrong down here. What did I do? Oh, 4. So this says, what do I need to raise 2 to get 16? Well, 2 to the 4th power is 16. The next one, log base 3 of 27 equals 3. So this is the base, so I'm going to take 3. I'm going to raise it to the 3rd power, and I get 27. So these switch, the base stays on the left-hand side, and the other things switch sides. Okay, number 9. So we have e cubed equals 20.0855. Well, the base here is e, so you could say it's log base e of 20.0855 equals 3, but log base e is the natural log. So that's the answer. What that's saying is, what do I need to raise e to get 20.0855? And the answer is e cubed is 20.80855. The next one goes the other way. So again, the natural logarithm is the log base e. So again, the base is e. The exponent is 2. The answer is 7.3891. E squared, 2.81828 squared is 7.36891. Okay. The next one says use the change of base formula. So some people might have got the right answer, but they didn't use the right method. So remember, there's two ways you can use the natural log. So what you do is you divide by the natural log of the base that we're interested in. So you divide by the natural log of 5 and you take the natural log of 24, or you could do log base 10, which is also on your calculator. Either one would be okay. And that's just because these two functions are easily on your calculator. I think somebody might have had a calculator that did this, and they might have gotten the right answer, but it wasn't using the change of base formula. So, okay, now we go into solving some exponential and logarithmic expressions. So because when you have exponential equations, you can always use the natural logarithm. You could use log base 3, but your calculator doesn't have that on it, so just stick with the natural log. So you take the natural log of both sides and then use the exponential property of logarithms, so you can bring the exponent out, and then you can divide both sides by the natural log of 3 to get that off of that side. And then you can add 2.5 to both sides, so it's 2.5 plus the natural log of 24 divided by the natural log of 3, which is 5.39. So I'll just stop for a second. So remember, any of these ones that are exponential problems, we have a couple more of them. You use the natural log. When it comes to the other way, when you've got logarithms and you've got an unknown, then you have to use the specific base that's in the logarithm to solve for it. But when it comes to the exponential equations, it doesn't matter. Okay, so that was 12. 13 was this. We're contracting. So it's opposite of problem number 6. So the first thing you do is you move the exponents in, the coefficients in, and make them exponents. So you get that. And then once you've got either just plus or minus in front of the term, then you can combine them together. The positive ones are in the numerator, and the negative ones are in the denominator. 14, the answer is does not exist. You can't take the natural log or the log of a negative number. So there's no, the domain is all positive real numbers. Okay. Next one. So there's two ways you could think about this. I can either take this exponent out or I could move this exponent in. Well, because if I take the exponent out, I'm just going to end up with a natural log of e. That makes more sense. If I guess you could still solve it the other way. I'm not sure. We'll try it in a second. But what you should have done is taken the exponents out. And the natural log of e is 1. So these both become 1, so you get 15 minus 14, which is 1. Now if you did it the other way, you'd have the natural log of e to the 15th power minus the natural log of e to the 14th power. Now you could combine those together and you'd get the natural log of e to the 15th power divided by e to the 14th power, which would be the natural log of e, because the properties of exponents, you would subtract this from that. 15 minus 14 is 1, and that equals 1. So, I guess 6 and 1/2 does. I think the person who did it this way didn't simplify it correctly. But that would be the way that, so they're actually about the same difficulty, but they both end up with the same result, which is 1. Okay. Now we have one. This is similar to the one we did earlier, except a little easier. So again, when you have an exponential equation, you just use the natural log. And that's because the properties of exponents here for logarithms say that you can bring out the exponent. And then all we have to do is divide both sides by the natural log of 5. And you get 0.75. Now somebody got the right answer. I don't know how, because they just wrote down the answer, which indicated they may have just tried a bunch of different numbers and did it by trial and error. But that's, we talked about a specific method in class, so I didn't buy that too much, I don't think. Yeah, the next two are, I think, I might have let you get away with it, but so the same thing here. Natural log of 2 to the x is the natural log of 1024, and I mean you could rewrite 1024 as 2 to the 10th power if you recognize that, but that takes some insight. This is much easier from just a standard. Stick it in your calculator. So bring the exponent out, divide both sides by the natural log of 2, and you plug that in your calculator and you get 10. And you can check it by 2 to the 10th power is 1024. Okay, now we finally have one of these logarithms where we have a logarithmic equation instead of an exponential equation. Here you do have to use the base that's in the logarithm. So we'll take 6 to the log base 6 of x and 6 to the 5th power. So the inverse properties of logarithms and exponents when the base is the same says that the left-hand side is just x. And 6 to the 5th power is 7,776. Yeah, I've had this problem before. I've given this problem, and I thought I was trying to be more clear, but it still didn't help anybody out. The next one. So you've got the population is 548,000 e to the kt. So it says the population in thousands. So it's 548,000, but I don't put in the thousand. I just put it as 548 in thousands. And that's why if you look at in 2005, which is t equals 5 years relative to year 2000. So 2000 is t equals 0. So it's t equals 5. And what we do is, so we're going to say P of 5, the population of 5 years is 650,000. So I'm just using 650, not 650,000. So you can use this to find K, and once you know K, then you can plug T in, which is T equals 10, to get the answer. So the first part is to solve for K. So you get 650, not 650,000. So that's the equation. Now, if the only mistake you made was just reading that incorrectly, then I didn't take too many points off. Okay, so you divide both sides by 548 and get my calculator out. Finally have to use a calculator. So 650 divided by 548 is 1.186. So again, it's an exponential unknown, so we're going to take the natural log of e to the k, and t is 5, I forgot to do that, is equal to the natural log of 1.186. So here the inverse properties of logarithms and exponents, I get 5k, k times 5 or 5k, is equal to the natural log of 1.186, or k is the natural log of 1.186 divided by 5. And that turns out to be 0.03414. So we use the population at 5 years relative to 0 years to find k. And then once you have k, we can say that this population P of t is 548,000 times k, which is 0.03414 times t. And then we evaluate the population at 10 years, t equals 10. So you just plug that in your calculator and you get 771,000. And that kind of makes sense. I mean, 10 years going from 548,000 to 771,000. That seems like a reasonable rate of increase. Okay, the next one is you just using the formula basically. So R was the interest rate, which remember you have to use the decimal equivalent. And what did I say it was? 6%. So it's 0.06. The original amount was 10,000. The amount was 20,000. So you stick those in, you get 20,000 is equal to 10,000 times e to the 0.06 times t. So now you just got to solve for t. So you've got, if you divide both sides by 10,000, you get 2 equals e to the 0.06 t. Then you take the natural log of both sides. So the left-hand side is natural log of 2, and the right-hand side is 0.06 t. So t is the natural log of 2 divided by 0.06, which is 11.6 years. So if you had an account, to double to double the amount of money that you have in a savings account at 6% interest, it takes you 11.6 years. Now, things like stocks, historically stocks have been more like 11%. And so the difference would be if you had 11%, you'd have this number would be 0.11 instead of 0.06. And you see it's about half. So it will only take five or 6 years to double the amount of money that you have. That's why when you have a stock market that's continuing to grow at a healthy rate, you can make a lot of money quickly, but you can also lose a lot of money quickly too. Okay. The next one was the natural log of x minus the natural log of x minus 2, I think. This was the one I got wrong initially, and I fixed it. So is that right? That's the fixed version. Yep. So that equals 2. So you combine the two terms by using the properties of logarithms. So because that's negative, you divide by that. And then you would use, this is a logarithmic expression, so you take the base of the logarithm, which is the natural log. So you do it e as the base. So you do e to the natural log of x minus 2 is equal to e squared. E to the natural log of something is just that something. And e squared is 7.389. So you multiply both sides by x minus 2. Multiply that out, so you get 7.389x minus 14.778. That's this times 2. And then you subtract this from both sides, so you get negative 6. So 1 minus 7.389 is negative 6.389. And the right-hand side term here just stays the same. And you divide both sides by negative 6.389, and you get x equals 2.313. And then finally, we have another logarithmic equation. So you always have to get the natural log by itself. So we got this 3, we got a 7. So the first thing we're going to do is we're going to subtract 7 from both sides. That'll give you 2. 9 minus 7 is 2. And that should be 3 in front of the natural log here. Okay, now we've got the 3. We need to get rid of that. So we divide both sides by 3. So we get that. And we use the same base for the exponential as the logarithm. So we can use the inverse properties of exponentials and logarithms. So you get 5x is equal to e to the 3/2 power, which is 1.9477. And divide both sides by 5, and you get 0.3895. So that's the last one. Now, the exam is going to probably be equal parts of each one of the sections that we covered. So, 25% will be the last stuff we covered, and then probably 25% from chapter 1 and 2 and 3. Anybody got any questions about any of those problems? Now, I'm not going to put anything more difficult on the exam than's on the test. So just that's why it's probably a good thing to go back, and now that I've worked through this, go back and see what you don't think you can't do without some help. You could go back to the review, because I go through every one of these kinds of problems, and you can see if you can learn it that way. There's not much point spending time on stuff you already know. Okay, so that is test number 2. So let's look at, that's test number 3. Test number 2. So if you have that and you want to pull it out and ask me anything, otherwise I will pick out some things that I think you just didn't know what the heck you're doing. Maybe even the ones that are what's that? So let me know if you'd like. What's that?
The first 2.
The first 2?
Like.
Oh, the first 2 there, yeah. Yeah, I mean those are. Did you have any?
I don't even know if I have test number 2 still.
Did I ever? I think I gave it back to you.
I think you did too, but I put it somewhere else. So I got.
Yeah. How about you, Brian? Anything?
It's not in.
I'll start, and you guys can. Yeah, a lot of people got problem number 2 right, which was it's an easy problem. So let me just make one up here. Okay, so this is first problem says write the complex quotient in standard form, and standard form just means that you don't have any imaginary parts in your denominator. So you always take the denominator and take the complex conjugate of the denominator. That means changing the imaginary part to the opposite sign. So it's positive 3i, so I make it negative 3i. And what that does is the imaginary parts are going to cancel out because you're going to have plus 3i times 3, which is plus 9i, and you're going to have negative 3i times 3, which is negative. So the only parts you have are the first parts and the second part. So here you get 3 times 3, which is 3 squared, and here you get 3 times 3, which is 3 squared, and I times I, which is I squared, and then positive times negative. So you get 3 squared plus 3 squared, I squared. Now in the numerator, nothing drops out, so you just use FOIL. So you get 12 minus 6i from here, minus 12i from the outside, and plus 6i squared here, because you get negative 2 times negative 3 is positive 6, and then I times I is I squared. So at that point, the next thing you do, we can go ahead and combine the two imaginary parts. So negative 6 minus 12 is negative 18. When you get I squared is negative 1. So this becomes positive 6i squared is negative 6. The same thing applies in the denominator. Here we have 3 squared, which is 9, and then we have 3 squared, which is 9, negative I squared, but I squared is negative 1, so this part here becomes negative 1, so we get a plus 9. And that's going to happen, I think.
Well, no, is it just because I have 3 plus 3? Yeah, it's because I have 3 plus 3. So, but
the first and the last terms are the ones that don't get canceled out, and they both become real because you have, the I squared, two imaginary numbers multiplied together give you a real number when it turns out that they're I. So the rest of it is just simplification. So you'd have 12 minus 6 would be 6 minus 18i divided by 18. And you look to see if you can simplify it, if there's a common factor, which there is, which is 6. So if I divide everything by 6, I'll get 1 minus 3i over 3. So always look to see if you can simplify the, you may or may not, depending upon what I end up picking. Anybody got any questions on that one? Now, the second problem, let me just give you an example here. And really all that matters is what is the first and the last term. So you got 5 and you got 3. And what you do is you look at the factors of these two individually. So the factors of 5 are 5 and 1, and the factors of 3 are 3 and 1. So the possible rational zeros are going to be the ratio of, let's see which one's the numerator. This one's the numerator, and this one's the denominator. So you have plus or minus 1 and plus or minus 3 divided by plus or minus 1 and plus or minus 5. And then from this, you kind of have to look at all the combinations that you can come up with in terms of fractions and eliminate any that may be duplicates. So you can see that in this case, it's pretty straightforward. You've got 1 over 1, which is 1. So you got plus or minus 1 from here. Here you'd have 3 over 1, which would give you plus or minus 3. And then you now use this as your denominator. Instead of 1 being the denominator, it's 5. So you get plus or minus 1/5 using this and that. And then you'd get plus or minus 3/5 from that. And, if I give you a problem like this, I'll give you one where, these are going to be different. Neither one's going to be 1 because that's just too easy. So you're going to end up with at least 2 factors. You might even have 3. If the first term were 6 instead of 5, then you'd have actually, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. You actually have 4 possible denominators, which would make the whole thing a lot more complex because you probably have some duplicates. But that's what I'm looking for. You can go back and look at the notes, but it's basically looking at the first and the last term and the factors associated with those. Okay. Now, any other particular problems, or do you want me to just pick ones out I remember people not doing so well? I mean, completing the square, you should, I was talking to Ms. Pratt, and I was saying nobody appreciates why we do completing the square until about this time in calculus. We're using completing the square, and so it's an important skill to learn if you're going to take calculus. So as simple as it may seem, or you might say, oh, I could just use the quadratic formula. Why do I need to do that? Well, because the quadratic formula doesn't help you when it comes to this part of the year in calculus. So let's just do one for you. So you got x squared, say minus 6x minus 20. Okay. The key thing is I'm trying to give you real zeros. So if I put a positive sign in here, that's going to mess us all up, I think, because you'll end up trying to take a square root of a negative number. So when you actually solve for that. So remember, the zeros are the x values which cause the function to be equal to 0. So you set the function equal to 0, and you got to figure out what x values make this go to 0. So you take the two parts that have the variable and you separate those from the part that's the constant. Then you take the coefficient in front of x and you divide by 2 and you square it. So you get negative 3 squared, which is 9. So that's the thing we add. We add 9 and we subtract 9 because we want to keep it equal to 0. So originally this is 0. So if you take 0 plus 9 and minus 9, you still have 0. So, but because of this procedure, I can take these three terms and I can collapse them into a complete square. So this is the same as that. If I multiply this out using FOIL, I'll get that. And then I have the other two terms combined together. And again, to get real zeros, this has to be negative after I've done this process. So I end up with a positive, then I'd have two imaginary zeros, which that's acceptable, but it's not what we normally worry about. So now we're trying to solve, once you get to this point, you solve for x. So you add 29 to both sides. Take the square root, and you got to make sure you do the plus or minus on the left-hand side. You don't have to do it on the right-hand side. And then you add 3, so you get the answers 3 plus or minus the square root of 29. So those are your zeros. X equals 3 plus the square root of 29, and x equals 3 minus the square root of 29. And one thing is that you could also, if you remember back to quadratic functions, that to get it in standard form, you have to use the same procedure. If I, instead of setting equal to 0, if I just had the function as this, y equals this would be a parabola with the vertex at x equals 3 and y equals negative 29. The zeros would be those two. Those would be the x-intercepts. The y-intercept would be negative 20. You go back to the original equation and set x equal to 0. So this whole completing the square thing is an important thing for finding the standard form of quadratic equations, as well as for finding zeros, and also when it comes to calculus. So, we could use the same example. I mentioned it, but let's go ahead and not only find, in this case I asked you to find the zeros, but let's go ahead and plot this function, because that's the next problem. It's just a different problem. It's just so let me add a page. So when you're asked to plot something, if you look at the next problem, it says calculate the x and y intercepts, the vertex, the equation for the axis of symmetry. So let's do that for this particular function that we just found the zeros for. So let's move this thing up. So the original function was I forgot what it was, x squared minus 6x minus 20. So the vertex, what did we say the vertex was? It's 3, negative 29. So I'm gonna have to change the scale of this thing to make it work. So let's make this negative 30, and we'll make this negative 10, positive 10, positive 30. So the vertex is going to be right down here. No, it's 3, right? So 1, 2, 3, negative 29. So that's my vertex. Negative 3, 29. Now the two x-intercepts are going to be 3, which is right here. You see that's right. That's why the 3 here is always the x-coordinate of the vertex. And then we're going to go plus or minus the square root of 29. So I have to figure out what that is. 29 square root. 5.4. So if you go 1, 2, 3, 4, 1, 2, 3, 4, 5.4, and 1, 2, 3, 4, 5.4, those are your x-intercepts. Oh, is it? Well, it is positive 3 because you got x minus 3. Well, that's the, yeah, so this is the vertex is, oh, I wrote it down. I see what you're saying. Yeah, I wrote it down wrong. I plotted it correctly. I wrote it down wrong. Thank you. Okay, so is that, uh, we have the y-intercept. If you go back to the original equation here, set x equal to 0. So the y-intercept is going to be equal to 0, negative 20. The x-intercepts are 3 plus the square root of 29, 0, and 3 minus the square root of 29, 0. Those are the points. So if we go to our plot here, negative 20 is going to be about 1, 2, 3, 4, 5, 6, about right there. And because of the symmetry around this point, I'm going 1, 2, 3 this direction. So I'm going to 1, 2, 3. That just gives me one extra point. So then you can draw your parabola in there. So again, both the x-intercepts and the vertex required us to use completing the square. The y-intercept is a piece of cake. It's just the constant term in the original non-standard form, just the regular form, general form. If you didn't plot this one, I wouldn't take anything off for it, but it does give you a little extra point of reference to make so you draw a nice symmetric parabola around that. Okay, let's see what else we got here. Long division. What we got here? 157. Okay. Let's do another long division. Let's do a long division example. So let's do x cubed minus plus 4x squared minus 11x plus 15 divided by x plus 2. Now this one you could use long division or synthetic division. So we might try both ways, see if we get the same answer. It's easier to do synthetic division, so it's probably less likely to mess up. But we'll do both just for practice. Now, if you have any terms missing, which we don't, make sure you put a 0 in for it, because you need the space, you need the place. So we're asking the question, what do I need to multiply x by, the largest term here, highest order term, to get this term? So I say, okay, x squared times x equals x cubed. So I put that over top of the x squared column. And then I multiply it out. So x squared times x is x cubed. X squared times 2 is 2x squared. Then I put the negative sign here and put parentheses around the whole thing to remind me so I don't mess this up, which people still do because they don't listen to me. These cancel out and go to 0. That's the whole idea. And then you have 4x squared minus 2x squared. So that's 4 minus 2 is 2. And then we'll bring the next term down. Now we ask the next question, which is going to be the next smaller term. What do I need to multiply x by to get 2x squared? The answer is 2x. So we take 2x times 2x, that gives us 2x squared. We're doing the right thing. And we finish off 2x times 2, that's 4x. Put our negative sign, little parentheses. Add these two together, you get 0. Again, that's the whole purpose. And you get 11, negative 11 minus 4, so that's negative 15. And our final term, what do we need to multiply x by to get negative 15x? So the answer is negative 15. So negative 15 times x is negative 15x. Let's go ahead and bring this next term down. So, and then negative 15 times 2 is negative 30. Again, we're going to subtract it. So negative 15x plus 15x is 0. 15 minus a negative 30, that's plus 30, so you get 45. So that's my remainder. So the question is, well, there's two questions. What does this reduce to? What it actually reduces it to, the original function is going to be this, x squared plus 2x minus 15 plus the remainder divided by the original denominator. So you get that. So that's the answer I'm looking for, not just finishing the whole thing out. And then it says, what does the value of the remainder represent? Well, what it represents is that if you evaluate the function at the zero associated with this factor, which is negative 2, it's going to equal 45. So if I plugged in negative 2 into this equation, I'll get 45. That's what I'm looking for. The remainder is not, what does the value of the remainder represent? Well, it equals 45, but it represents the value of the function at x equals negative 2. Now let's go ahead and use synthetic division. And when you use synthetic division, you don't use plus 2, you use negative 2. It's the 0 associated with the factor. Okay, so we bring this one down. Negative 2 times 1 is negative 2. 4 plus negative 2 is 2. Negative 2 times 4 is negative 4. Negative 11 plus negative 4 is negative 15. Negative 2 times negative 15 is positive 30. 15 plus 30 is 45. So there you go. So the answer is x squared plus 2x minus 15 plus the remainder divided by the original denominator, which is the same answer we got doing it the other way, a little faster. And again, what 45 represents is the value of the function at x equals negative 2. So that example covers both synthetic and long division. I probably won't give you one that has a squared. I'll make it a nice linear term if I put it on the exam. I probably will not put a problem like, even though I'd like to, but I'm not going to do it. Problem number 10, which is where you have to use, there I give you one of the complex roots. You have to find the other complex root, and then multiply them together to get since you got enough on the exam, so don't worry about that. Okay, I think there'll definitely be a problem like number 8, which is where I give you one of the zeros and you have to find the other two zeros. Now, I don't have a problem in my head, so I'm going to make one up here. So this is what I would do for a test. I just make up a third order equation. Now, I can't have these numbers too far apart, or the graph gets really huge. So I'd probably pick them to be fairly small, so that when I multiply these things together, they don't get too big. 1 times negative 2 times 3. So what I'm doing is making the problem, and then we'll figure out how we solve it. I'm not going to give you the answer ultimately, but I need to make up a problem. So if you multiply these two together, you would get that. And then if you multiply by x plus 3 like that, you get this times all three of those, you get x cubed minus x squared minus 2x, and then you multiply by 3, so you get 3x squared minus 3x minus 6. So we add all this together, get x cubed plus 2x squared minus 5x minus 6. Okay, so that's what I would give you. I'm not going to. We know the answers over there, but so we know why we're going. But and what I would do is I would give you. I'd say one of the zeros is x equals 2. So you're given 1, 0. So what that allows you to do is to find the other two zeros. So the way you do that is we can use synthetic division, because that's the easiest way to do it. So remember, the 0 is x equals 2, the factor is x minus 2. So that's where I got that number from. I took that factor and I made it into a 0. Now when it comes to synthetic division, we use the 0, not the factor. So we're going to put the 2 there. So you bring the 1 down, 2 times 1 is 2, 2 plus 2 is 4, 2 times 4 is 8, 8 minus 5 is 3, 2 times 3 is 6, negative 6 plus 6 is 0. So that means that is a 0, because anytime you get a 0 remainder, that means that your original number here is a 0. X equals 2 is a 0. Therefore, x minus 2 is a factor. And the remaining three numbers, you can write the resulting quadratic equation, which you can factor. Or you could use, if you can't factor it, by looking at it, you could use completing the square or something like that. But I'll give you one that you should be able to just look at it and factor. So we know the two numbers multiplied together have to be 3. Well, that's easy because there's only two numbers that make that happen. And because this is positive, for this to be positive 3, they have to be both either negative or positive. But because this is positive, that means they both have to be positive. So those are my other two factors. My third factor was x minus 2. Okay, because I gave you the 0, so that gives you the factor. So what does that mean? Now if I want to plot it, the x-intercepts are the zeros. So I have x equals -1, x equals -3, and x equals +2. So those are my x values. The actual x-intercepts would be -1, 0, -3, 0, 2, 0. So those are the coordinates. So I've got the x-intercepts for third order equations. I really only have three things. I have the x-intercepts, I have the y-intercept, and I have the end behavior. So I need the y-intercept. Well, that's easy. You set x equal to 0. You look at the original equation, and you get y equals -6, or 0, -6. So that's the coordinates of your y-intercept. And then the only other thing you have is the end behavior. And because this is positive, we know that it's going to start down here and it's going to end going up that direction. So with those three things, we can get a piece of graph paper and plot this thing. So we've got the three x-intercepts, which are -3, 0, -1, 0, 2, 0. We've got a y-intercept of -6, which should be right here. with this particular scaling. And we know the function has to come down from here, goes up here somewhere, comes back down, goes through there, comes back up. And so, it doesn't have to be perfect. It does have to pass through these 4 points. Whether you overshot, the reason I overshot here is because it's probably going to be close to the midpoint between the two intercepts where you're going to have the minimum, but you don't know that for sure. So as long as you've passed through this point, that'd be fine. And so, if you could have the same function, if everything was negative, then it would come from the other direction. It would still go through those 3 points. The y-intercept would become positive 6 instead of negative 6. So if I looked at, this original equation, it was negative x cubed minus 2x squared plus 5x plus 6. It would look exactly the same, except it would come down like this, come up like that, go through positive 6, come back down like that. Okay, last thing, we'll talk about rational functions. There'll probably be a plot of some rational function on there. So it's probably going to be like the one on the back. And it won't be, it's not going to be too complicated. It's going to have just 2 linear parts to them. So let me make one up here again. So let's say we have 2x plus 8 divided by x minus 2. So that's the rational function. So there's 4 things we have to worry about with rational functions. There's x-intercepts, y-intercept, vertical asymptote. In this case, this is going to be 1 because it's just one factor in the denominator, and the horizontal asymptote, and maybe one additional point. Now, I'm not sure what that additional point is yet because I haven't plotted this thing. Okay, so let's go through the list here. The x-intercept. You set the numerator equal to 0. Okay. So if you solve for x, you'll get x is negative 4. So that's the x-intercept. It's negative 4 comma 0. The y-intercept, that's f of 0. So you get 2 times 0 plus 8 divided by 0 minus 2, which is also negative 4, but it's y. So there it's 0 comma negative 4. So that's my y-intercept. Then you have your vertical asymptotes. There, to find the x-intercept, we set the numerator equal to 0. To find the vertical asymptote, you set the denominator equal to 0. So you get x equals 2, and that's a line. It's not a point. So we use the functions. Here we have a point. Here we have a point. Here we have a line. And then the horizontal asymptote, you take the ratio of the leading coefficients of the highest order term. So, and it's a line, it's a horizontal line, and it'll be 2 divided by 1, whatever these are. So that's 2. So it's y equals 2. So that's a line, horizontal line, vertical line. So we're going to plot this, and we're going to say, okay, there's probably one additional point. I'll tell you which point to plot. So let me get a piece of paper. So let's plot what we got. Plot what we got. Okay, so you got negative 4 and negative 4. So the y-intercept is negative 4. The x-intercept is negative 4. I'll put a scale on here. Okay. And then we have a vertical asymptote at 2. That's a vertical line, as the name implies. Whoops. And then we have a horizontal asymptote, which is also 2. How about that? So here's my horizontal asymptote. So the question is, where do I need a point? Well, obviously I don't need a point over here because I've got 2 points. So I probably need one up here. So I'm going to say evaluate at x equals, let's pick 4. Like I said, I'll tell you where to evaluate it. So you go back to your original equation, which I've forgotten what it is. So you do f of 4. So that's 2 times 4 plus 8 divided by 4 minus 2. So x minus 2. So that's 16 divided by 2, so it's 8. So what we have is a point, 4 comma 8. So that's the point I'm going to plot on my graph. 1, 2, 3, 4, 8. 1, 2, 3, 4, 5, 7, 8. Okay, so there's my point. So now, this thing's going to come from this horizontal asymptote. It's going to go through this point, and then approach this vertical asymptote. Now, because I only have a single factor in the denominator, this thing's going to go from negative infinity up to positive infinity, and it's going to come down, and it's going to go like that, and then it's going to turn before it gets to the horizontal asymptote. So that's what it looks like. So we got an x-intercept, a y-intercept, an extra point, vertical asymptote, and a horizontal asymptote. And there's probably another point here, like about there, that would be symmetric. That would be another point that you could put in to maybe draw better, but I wouldn't ask you to do that. So I'm definitely going to put something like that on there because that covers all the stuff, and it'll be a simple rational function like this. So if you look at your test, that's what it looks like. Your retest looks like that. It'll be on the exam like that, but it covers all the main points. So we've kind of done a quick review here. If you wanted a little longer review, you can go back and watch the review from second test if you wanted more examples. It doesn't mean that if I didn't talk about it yet today from that chapter 2 stuff that it's not going to be on there, but probably most of the stuff I talked about today will be on there. And I'll post one additional video which will be giving you probably 2 examples solving simultaneous equations, one using substitution and one using the matrix method, and that'll be the final chapter stuff. So the test, if you can't take the test on Thursday, let me know and I'll put it in the testing center, but you have to take it before Thursday if you have some other conflict. And if you want to get any credit for any homework that you haven't already done, you need to turn that in at the exam. And yes, go ahead. It will be in here. Yep. Okay, so that's it. Remember that you can do a course evaluation if you're interested. Just go into Canvas and click on the icon. And hopefully I'm still recording class. Yep, good. Stop.